we go, talking a little bit about funky functions in this unit, and today we're going to start off with composition of functions. So first of all, a composite function really is just a combination. Remember, whenever you see composite, it really just means a combo of two or more. All right, so we're also going to look at the domain and the range of a composition of functions. And a function composition, or simply just stated as composition, is this operation noted by this little circle. So up here when you see this G little circle F, that represents the composition function, and it's read as f of G of x. Or another way that you're going to see that is in this G of f of x with the parentheses. That's known as the function notation. All right, now there's two ways to write composite functions. You can use mapping notation. So that's G of f colon x and then the arrow. Arrow represents that mapping notation. And the function notation, or the f of x notation, simply goes G of f of x. And it always represents this G of f of x. I feel like I've said that 3 or 4 times already. And the way this whole thing works, this composite function, is really what you're doing is you're evaluating a function from the output of another function. So you've maybe seen the function machine before, where we have the inputs, our domain, or our x values. So for example, let's just take the x value of 1. We're going to input that into our first function, and that in this case is going to be f of x. We'll run it through the rule, so we'll say it's f of 1. That means it's 1 plus 5, which the output of that is 6. Now that result we're going to take and run through the next function, which is g of x, and in this case we made our rule x squared, so it's going to take the input, which is the output of f of x, and run it through its rule and square it. So 6 squared in this case would be 36. So we would say g of f of x, in this case, when we evaluate that for 1, results in 36. All right, that sounds a little bit confusing, but I think you'll pick up on it. Let's try a few examples. In example 1, we are given the function f of x is 4x squared and g of x is x plus 7. We want to evaluate f of g of 3. So always keep this in mind. We're going to work from the inside out. So the first function we're going to evaluate is the function g for 3. So let's evaluate g of 3. It is equal to 3 plus 7, and that results in 10. Now we'll take the output from g of 3 and we'll evaluate it for the function f. So we're going to evaluate f of 10, which we'll put that into that rule, and that's 4 times 10 squared. 10 squared is 100, and 4 times 100 is 400. So we say f of g of 3, is equal to 400. All right, let's try another example. Now we're going to evaluate g of f of 3. So again, we're working from the inside out, so we're going to evaluate the function f first for its value of 3. So we're going to say f of 3 is equal to 4 times 3 squared. Well, 3 squared is 9 times 4, that's 36. So the output of f of 3 is 36. We're going to put that into the function g. So g of 36 is equal to 36 plus 7, which results in 43. So we would say the g of f of 3 is equal to 43. Now part C just says, based on parts A and B, do you think composition of functions is commutative? In other words, can we swap the order in which we're multiplying these functions by? So based on the outputs here, we have 400 for f of g of 3 and 43 for g of f of 3. We're going to say no, it's not commutative. All right, let's take a look at example 2. In example 2, we have the same functions, f of x and g of x. However, now we're asked to write an expression for f of g of x. Now, this sounds a little bit tricky, but all you're doing is you're going to take the expression for g of x and substitute it into the function f of x wherever you see that x. So what we're taking and evaluating is f of x plus 7, where this expression x plus 7 is our x value. So f of x is 4 times x, but our x is x plus 7. So we're going to substitute the expression x plus 7 in and square it. All right, now here is the expression for f of g of x. We should simplify this further. So x plus 7 is really, x plus 7 squared is really x plus 7 times x plus 7. So we need to distribute our x's and our 7. When we do that, we'll get 4 times x squared plus 14x plus 49. And now we need to distribute that 4 to all those terms. So the result there is 4x squared plus 56x plus 196. Now that is the new expression for f of g of x. All right, now let's switch that around and let's write the expression for g of f of x. So keep in mind now, we're just going to go the other way. We're going to take our function for f of x, which is 4x squared, and we're going to substitute it into the expression g of x wherever we see the x. So we're going to say it is g of 4x squared, and our function for g is x plus 7. However, the x is 4x squared, so it'll be 4x squared plus 7. Now, there's no simplifying we need to do, so here is our expression for g of f of x, which is 4x squared plus 7. All right, let's get a little bit more practice with this because this can be tricky. Evaluate f of g of 3, so now we're going back to evaluating an actual number. We're going to work our inside out. So we're going to evaluate g of 3 first. So g of 3 is 3 times 3 squared, results in 27. And then we're going to take that 27 and put it into our function for f. So that's 27 minus 2, which is 25. So f of g of 3 is equal to 25. All right, now let's write an expression for g of f of x. So remember, this is f of x. X minus 2 is going to be substituted into the expression for g of x wherever you see an x. So we're going to say this is really equal to g of x minus 2. This is our x now, and our g function is 3 times x squared. But our x is x minus 2, so it becomes 3 times x minus 2 squared. Just like in the previous example, we're going to expand the x minus 2 to simplify that. So I need to distribute all those terms. That becomes 3 times x squared minus 4x plus 4. Now we need to distribute the 3 to all those terms, and we get 3x squared minus 12x plus 12. And this is our expression for g of f of x. All right, now let's move into talking about the domain. Remember, your domain are your set of inputs. What works for your function here? So let's evaluate each one of these domains by itself first, and then that will give us some insight into what the domain for r of f of x is. The domain for f of x is all reals. This is quadratic, and we know quadratic takes all reals. And the domain for r, though, if you take a look at r, is going to be all reals as well. However, it's not going to include 0. So it's all reals except 0 because we cannot divide by 0. That would make that term undefined. All right, so let's write an expression for r of f of x and figure out what its domain is equal to. So r of f of x, we're going to take f of x, which is x squared minus 4, and substitute it into our equation for r wherever we see our x. So that's equal to 1 over x squared minus 4. Here is our r of f of x. And now evaluating the domain, remember, we cannot let our denominator, x squared minus 4, equal 0. So what values of x would make this x squared minus 4 equal to 0? Well, let's solve for this. You get x squared, you got to bump your 4 over, take the square root, and x would be equal to plus or minus 2. Therefore, x cannot be equal to plus or minus 2 because if it were, then our denominator would be equal to 0, and that would make our function r of f of x undefined. So we say our domain is where x cannot be equal to positive 2 or negative 2. Therefore, the domain is all reals not equal to positive 2 or negative 2. All right, let's do an application to this type of function. We see that the Le Mans car dealership has two incentives for buyers. They give a 12% discount off the sticker price as well as a $2,000 rebate at the end of the year. So if you were given the choice, which would you choose first? Would you take the incentive first or would you take the rebate first? Well, let's write let's write a function for the discount. So the discount, g of x, would be equal to x minus, not x minus, it's going to be, the discount is 12% off. So if it's 12% off, then it's 88% on, which means you're really only going to pay 88% of the car's value, not 100% of the car's value. All right, now let's write a function, r of x, for the rebate. Keep in mind here, x represents the sticker price. So the rebate would be our sticker price minus $2,000. All right, so here's two distinct functions based off of x, the sticker price of the car. Now it says if the sticker price is $33,000, which incentive would you take first, the discount or the rebate? So let's find r of d of x first. We're going to take this 0.88x and put it into r of x, 4x, and therefore we're left with 0.88x minus 2,000. And then let's go and find d of r of x. So now we're going to take r of x and plug it in here, and it becomes 0.88 times x minus 2,000. All right, now let's evaluate each one of these for a value of $33,000. That's a nice car. All right. When we take 0.88 of 33,000 and subtract 2,000, I'm going to check my notes, but we get $27,040. And when we take our 0.88 and we subtract our 2,000 from our 33,000 first, we end up with $27,280. So it looks like you're going to pay about $240 more if you take the rebate first and then the discount. However, if you take the discount first and then the rebate, you're in the money.